Imagine a steel beam suspended in a frictionless, empty void. If a force strikes it dead center, it doesn't bend or absorb the load, it just instantly accelerates and spins out into space. When we assemble a global set of finite element equations for a structure, we haven't actually built a functional model yet. We've just mathematically described that free-floating beam. Force equals stiffness matrix K multiplied by displacement vector U. The K matrix expands into a 6x6 grid. Because the beam can move infinitely, it is flagged as a singular matrix with a determinant of 0. Algebraic inversion fails. The math cannot resolve infinite motion. To stop this rigid body motion and actually see how the beam deforms, we have to tie it down to something. We need physical constraints. In linear algebra, these physical boundary conditions are not abstract ideas. They are precise numerical values hard-coded to specific nodes on the structure. By pinning down these specific nodes, we provide the fixed references the solver needs to define relative deformation. The result is a stable, solvable system where every force has a measurable reaction. Let's ground this with a standard physical model, a cantilever beam, fixed solidly to a wall on its left side at node 1. This is our 6x1 displacement vector, U. It lists alternating degrees of freedom, lateral deflection, v, and rotation, theta. The wall prevents node 1 from moving vertically, so v1 becomes exactly 0. It also prevents bending, so theta1 also becomes 0. The remaining 4 degrees of freedom on the beam are completely free to move according to the external forces applied. Watch what happens when we execute matrix multiplication between the stiffness matrix and this updated displacement vector. Following the rules of algebra, column 1 multiplies by v1 and column 2 by theta1. Since both are 0, those two columns are entirely neutralized. But we have to look at the other side of the equation, the force vector at node 1. Because the wall rigidly holds the beam, it pushes and twists back. The reaction force P1 and moment M1 are entirely unknown. This creates an algebraic deadlock. We have equations where both the applied force and the resulting displacement are completely unknown. To break the deadlock, we sever the system of equations horizontally to separate knowns from unknowns. We extract only the bottom 4 rows where applied forces are known. This isolated block forms our primary set of equations. This newly formed 4x4 primary set is mathematically stable. It can now be inverted to solve for the 4 unknown deflections. By deliberately partitioning the matrix, we purge the unsolvable reaction constraints, creating a condensed, invertible core that reveals exactly how the structure deforms. Different physical supports require a different matrix reduction logic. Consider a simply supported beam, pinned at the left end at node 1 and resting on a roller at the right end at node 3. Looking at our displacement vector, the left pin restricts vertical movement. Lateral deflection v1 drops to 0. The roller on the right also restricts vertical movement, so lateral deflection v3 is 0 as well. Notice a critical physical difference. Both supports allow the beam to pivot freely, so slopes remain unknown. We map the indexing constraint by counting down the vector. v1 sits at index 1, and v3 sits at index 5. Applying the 0 multiplication rule to the stiffness matrix using these specific indices, columns 1 and 5 are mathematically neutralized. Notice the primary set isn't a clean split. It is formed by extracting the remaining interior rows, 2, 3, 4, and 6. The 2 rows we pulled out, rows 1 and 5, contain the unknown vertical reaction forces at the 2 supports. We define these extracted rows as the secondary or auxiliary set of equations. The physical topology of the supports directly dictates the geometric shape of the solvable algebraic core within any finite element model. Here's the operational flowchart to solve finite element beam problems. Assemble the global matrix, apply boundary conditions, partition the matrix, and invert the primary set. Executing steps 1 through 4 successfully yields the global deflections and slopes of the loaded structure. But a structural engineering question remains. We discarded the support rows because the reaction forces were unknown. So how do we find out how much force the wall is actually taking? Recall the rows sliced away during the matrix partition phase. The displacement vector in this secondary equation still contains empty variable slots. We take the calculated numerical answers from our primary deflection solve and feed them directly into this discarded equation. Because all displacements in the vector are now known numerical values, standard matrix multiplication can be executed across the row. This final multiplication yields the exact physical reaction forces occurring at the boundary conditions. Knowing these reaction forces is what allows engineers to properly size the bolts, welds, or concrete anchors holding the structure together. This sequence of partitioning and substitution defines the operational logic of the industry. It is the literal code running inside modern commercial structural analysis software every time a model is calculated. Mastering matrix partitioning provides the mathematical link between theoretical mechanics and the actionable data required to build the world's infrastructure.